Hey, this is OXDF, and today we're doing Admin of Code 2022, Day 15, Beacon Exclusion Zone. There's a lot of story here. Basically, our puzzle input's going to look like this, where it gives us a sensor and a closest beacon. And we should, when we say closest, all of our distances here are going to be Manhattan distances. So it means like the distance in X plus the distance in Y, rather than like the actual diagonal distance. So worth noting. It's also worth noting that it says in here that the closest beacon is here. That means there's nothing else at that distance or less. There's no ties or etc. Like every other beacon is longer. Um, let's see. So you get something like this, and then, because this beacon, this S is here and this beacon's here, we know there are no other beacons in this area. Okay. So the challenge is going to be, they're going to tell us a row, and so in our real thing, it's going to be row 2 million, right? Yeah, 2 million. And the challenge is going to be look on that row and count how many spaces cannot have a beacon, by getting the overlapping sensors. Peeked at the puzzle input already. The numbers are huge. So in the example here, we're working in a space that's like 30 by 30 or something, And so that is pretty simple we could just track all the points, but we're not gonna be able to track all the points across the space. The space is too large. So we're gonna have to think of more creative ways to do it. Let's go ahead and jump over. I'll run my genday script here for day 15. And I went over, there's a link to the repo with all my code in the description here, as well as I do a little bit more of an intro into this script on the day 1 video. But in short, it pulls the input and gives me a little stub to work with. So there's not that many sensors. There's only 23 sensors, which is relatively small. The challenge is going to be just looking at these sizes and where the closest beacon is at negative 250,000. Here we're at 2 million. And so again, we can't, when we start talking about like 2 million by 2 million grids, or 4 million because we're going negative, 16 million, we're not going to track all those points in memory. It's too much. So we're going to have to think of smarter ways to do it. All right, let's go ahead and start on the puzzle itself. So what are we going to do? First thing I want is I'm going to make myself, just because it's going to come in handy, a dist function, which is going to take x1, x2, oh, no, sorry, let's make it x1, y1, x2, y2. That'll work. And all we're going to do is return abs x1 minus x2 plus abs y1 minus y2. Perfect. Now, that's not that complicated, but it's just going to come in handy to have that. So now, what are we going to do? We're going to read our lines in, and we are going to do for line in lines. And now for each line, first thing we have to do is parse it, right? So let's get the input here. We'll grab an example here. So we'll say like tokes equals line dot split on space. And so now we can say our sensor X is going to be, that's tokes 0, 1, 2, tokes 2, and then we could split this on equals or something, but I'm going to cheat a little bit and just say starting at position 2, so that's going to be the number here, and then we want to get rid of this comma at the end, so we'll do -1. And then this is all going to be an integer, so we'll turn that into an integer. We'll copy this, and we'll do it 4 more times. So we need sensor Y, and that is going to be the third one. We want beacon X, and that is going to be 3, 4, 5, 6, 7, 8. And we still need to chomp the comma at the end. We need to chomp the colon here. And then beacon Y is going to be tokes 9, and we actually don't need to chomp because there's no end thing here. Okay. It's gonna be, I think it's gonna be handy to have around. We're gonna say dist of sx, sy, bx, by. So now we'll have a d. So for each line, now we have a thing. So what are we gonna do here? If we think about our target row, and so let's go ahead and actually define that. Where are we going to do that? I guess down here. So we can say target row is going to be 2 million. And in Python, you can add underscores to numbers wherever you want, actually, but it just to help make it more readable. So I'm doing it here. And we'll make a target row empty equals a set. So now we're going to keep our points that are empty on that row. And the other thing we need to keep track of is target row beacons, because we're asked to come up with the number of empty spots on a target row. But if a spot has to be empty from one beacon, or if a spot on the row could be a beacon, and I'm trying to figure out how that actually is, but like here we have a beacon, and so when they count, they get the answer 26. That is, this whole distance is actually 27, but then they remove that beacon. So we want to keep track of beacons on the row. Okay, so we're now looping through. So we're going to come here and we'll say, we want to figure out the range from any given point. I should probably like draw this out. I didn't plan on this, but let's open up a paint program and take a quick look. All right, I did such a bad job drawing this out when I was trying to like do it while solving. I'm cutting in to redo this explanation part. So let's say we have, we'll go a pen, a kind of thick thing. So we have our point here right in the middle of the screen. And this can be any point in space. And we have our beacon. We'll make it like green. Let's put it like right here. So what this means is, let's say there is going to be, let's just say this is like 7 and 3, right? So that means if these are 7 and 3, that means that we can pick a zone out here like at 10. Let's draw a line here. So it's gonna be like this. Again, these are not gonna be necessarily to scale, but like this, and like this, right? And so where the Manhattan distance to each of these points is 10, including the point on the line here, and all of these places cannot have a beacon, right? So we now have some other target row, right? Let's say we really care about this row right here. So we know that this entire distance is 10. We know this distance is less than 10. So if we look at this distance right here, that's going to be the y position here, the absolute value of the difference between this y position and this y position. And we now know if we wanted to get if we want to get these edge points here, we know that this distance plus this distance, this orange line really goes here. I don't know why I drew it. Like, let's draw it in the right spot. We know that the orange line plus the orange line is going to equal 10, because that's what our distance is, all of these, right? So we can calculate this one, and then we can get what this range right here, and then we can add all of these spots to our, this is target y value can't be x, right? So let's go implement that in code. What that means is, I don't know if that diagram was actually useful, but like our y distance is going to be equal to the absolute value of the sensor y minus target row, right? So we now know the amount of the distance spent getting to the target row. So the remaining distance, the spaces that are the maximum x's, we'll say, is going to be d minus y dist. And so now we can say for I in range, I guess maybe not I is the wrong thing. We'll call it like dx in range of x dist. Actually, it's not x dist. It's going to be, let's see. Let's actually, nope, we're going to change this again. We're going to say for x in range from, and we'll say sensor x minus x dist, which is going to be, I already closed my, yeah. So sensor x minus the x distance is going to put us about right here. So we're going to go start here, and we're going to go to here. And we're going to go to sx plus x dist plus 1, because we want it to be inclusive. And so then across that whole row, we can just say target row empty dot add x, we don't need to track the y positions, we know the y positions. And so then we can say if beacon of y equals target row, we'll say target row beacons dot add, and again we just need bx here, so we'll add that. And so now this is giving us, this will loop through all the rows, and it will give us what we need here. It'll give us a list of a set of the empties on the target row, as well as the beacons on the target row. So now part one is just going to be len of target row empty minus len of target row beacons, and I think that's actually it. Let's give it a try. Python day 15 input.text. We got a number. Let's go put it in. Awesome. All right, I'm gonna pause to read and think here. Okay, so we're gonna work through a grid from 0, 0 to 4 million, 4 million. So again, still huge. We cannot track all the empties. It's gonna be ridiculous. So what we need to do is find a spot, find the single spot. Where does it say that? It says somewhere here that there's only one. Example above. There is only a single position that can have that beacon, and so I guess they say that in the example above. I'm assuming I find the only possible position for the distress beacon. Okay, yeah. So there's only one beacon, and the trick here is going to be to say that we know that that beacon must be. We can't search the whole space; it's too big. But we know that the beacon must fall exactly d+1 from one sensor, because if it was d+2 from a sensor, then the d+1 spot would also be in there, unless that was cut off by another sensor, which then it would be d+1. You know, so like it's going to be d+1 from at least one of the sensors, and so we're going to check all the d+1 spots, which is going to be a much smaller space. Back here on our diagram, instead of checking all these. Instead of trying to check a huge thing, we're just going to check linearly. So it's going to be basically like 4 times d, and that'll be a much more doable search space. So let's go ahead and try to put that into code. It's still going to be it's still very brute forcey. So I'm going to actually use functions for this, because I want to be able to just return when I find it. And then it's going to be a lot of loops, and I think it's going to break. I think it'll have like a lot of nested breaks otherwise. So we're going to say, let's come up here and we'll start to see. So we'll say like def, find, and what do they call it? I want to be grammatically correct here. Tuning frequency. Tuning freak. And we'll take in the list of sensors, which we'll need to create. Pass for now. So down here, let's go ahead and create a sensors equals set, because we're gonna need to use these sensors a couple times. So we're gonna make them down here, and we will say sensors dot add sx, sy, and d. Where we want all three of those things. Okay, so now we can say for sx, sy, d in sensors. We're going to loop over all of them. We are going to find, let's see. So we'll say for dx in range d+2. I say range d+2 because I want, so what we're gonna do is we want to find, where's my diagram? We want to get all the points along this line, one outside the line. And so we're gonna start at dx equals 0, and therefore y will be d+1 right here. And then we're gonna get dx is equal to 1, so we'll get, so y will be this point and this point up here. Then dx equal to 1, and it'll become these 2 points, etc. And actually, I should say for each one, we're actually going to have 4 points to look at. So for let's say we pick a dx right here of 7. That means this is going to be out here. We're going to calculate out here, up here, and up here. And so we want for the dx to go from 0 to d+1, including. So we add d+2 because we don't include, Python doesn't include the last number. So then we can say dy is going to be d plus 1 minus dx. And now we can say for x comma y in, and let's come up with some points here. What if this is too, this would be ugly. Let's say, well, we'll just do it here. So sx plus dx comma sy plus dy will be our first point to check, because we're going to check 4 points here, right? So we'll check that, and we're going to do sx, that's minus, and then this one will be minus, and then both will be minus. Okay. So that gives us, we're going to loop over those, they're going to loop over 4 different x's here, or 4 different points here. Now first, we can say, if not 0 less than, let's say 0 less than or equal to x less than or equal to 4 million. So if and 0 is less than or equal to y is less than or equal to 4, like that. So if we're outside of our rounds, we just don't care. Let's just continue. Go to the next spot. Now we're going to say, now we have a point. We have a point here. And we want to check, is it found by any of the sensors, or is it outside? I mean, I guess the thing is, can it exist by all the sensors? So I'm actually going to loop over all the sensors again. And again, that's going to get really confusing with nested loops. So we're going to create a function here. So we'll say if check point x, y, and sensors return. Now we know we found our point that's valid. So we're just going to return, and I believe it was 4 million times x plus y. Okay. Like that. So now we just need to, so we're going to loop through all of our possible one step outside of the range of take each sensor. We're going to start walking through and just finding possible points, and then we're going to check them. So now, as long as we can write this check function, we're going to be good. So def check point, we'll take x, y, and sensors. So what are we going to do here? We're going to say for sx, sy, d in sensors. So for each sensor, we're going to say if dist of x, y, sx, sy is less than or equal to d, so it falls within the range that the beacon can't be, we're going to return false. And if we get through if we reach this point right here where my on line 25 where my cursor is, that means we've checked every sensor, and at no point is this possible point within the exclusion radius. And so then we can return true. So that means now once we return true, we find our answer, we return our answer, and so we come down here and we just say, I already forgot what I called. What did I call this? Find tuning frequency. Beautiful. And it takes sensors. And so hopefully this doesn't take too long. I'm going to add a time in front of it just so we can see how long it takes. Part 1's very quick. Part 2, if this gets too long, I either hit some sort of infinite loop, or I'm going to have to go back and find, oh, not too bad. 10 seconds. I mean, that's slow in computing terms, but that's not terrible. Let's see if it's right, most importantly. Awesome. Okay, so in summary, the trick today was twofold. In the first step, we just looked at points. We kept a set of points that we wanted to count up on the target row. And in the second one, the real trick is just looking one spot away from a current beacon. And again, that's really taking advantage of the fact they said there can only be one open spot in this whole range. So I'm going to call it there. This was a really tricky problem. I cut out a lot of me thinking about part 2 before I started coding. So this was really challenging. Thanks for hanging out with me today, and I'll talk to you tomorrow. Bye.